Okay, I need to say it again. So in my first tutorial, I used the graphic user interface. It's a very simple truss problem, overhead hoist, and we did everything just using the graphic user interface, including the pre-processing and also see the result like displacement and results and stress. But that is just for the simple question. If we need to do something like optimization, it's much faster and easier to modify the parameter in the amplifier rather than using the graphic user interface. So today I'm going to talk about I will give some basic information about the amplifier and how to modify the amplifier. And also, I will use a fully stress design as an example to do a demonstration on ABAQUS. So this is a basic layout of amplifier. If a line starts with 1 star, it means heading information. So for example, I don't know how to move it. This one? Okay. So for example, the 1 star node, it means I will give node information. I will define node. And the star element means I will define element. And also define the solid section, define material. And if a line starts with 2 star, double star, it means it is comments. And ABAQUS will not read the line start with 2 star. It's just like in your MATLAB, you also use a percentage something as comment. It's just for your convenience, for your better understanding your program. And this is the, okay, it doesn't work. So this is a full amplifier, and I will talk about in detail one by one. So this is a definition of node. Star node, I will give node information. So if I ask you to define a node, how will you define it? Define a node. Coordinate, yes. So this is node number, node 101, and this is x coordinate, y coordinate, z coordinate. And node 102, same, x coordinate, y coordinate, z coordinate. Because this is our problem of class is a 2D problem, so all the z coordinates are 0. And this is how we define the element. It is the element number 11. And element 11 is collecting node 101 and 102. So 101, 102. It also means that my local coordinate of element 11 is from node 101 to 102. If I define in a way that 102, 101, it means x coordinate, local x coordinate is from 102 to 101. So in our problem, it doesn't matter if I define it 101, 102, or 102, 101. Doesn't matter without change. What? So, for example, right now I define it as 101, 102. But if I define it as 102, 101, will the result change? Sign will change? So I received some email from students this last weekend. I think you have a homework problem like this, right? And the fourth is like this. And some, you can define node as this. Node 1, node 2, 3, 4. Also, you can define node 1, 2, 3, 4 here. So in different definition, it can either be I define in this way local coordinate, local x direction, or I can define in this way. It's all depends on how you define the node. But in both ways, the result should be the same, right? The result of this problem shouldn't be depend on how you define the node. So in our problem, this starting node and ending node should not be a problem. You can define it any way you want. This is a definition of element. Heading information and echo yes, model yes, history yes, means echo means I will put the input information in the output database again. So it's echo yes. And model, I will print the model information in the output database. And history means that if you have several steps of analysis, I will put the result of each step in the output database. So if you turn this as a no, no, no here, it will only print out the minimum information in output database. And as I said, double star, started with double star is comments. So ABAQUS will skip it, just for your convenience. And so this element set frame. Frame is a name that you define when you use a graphic interface. So last time I didn't change any name. I used material 1, section 1, and job 1, right? But if it's a complicated problem and you have a lot of parts, you can define the name yourself. And this is name frame here. And for example, if I define all these 11 to 17 as frame, then the frame, this element set will have the sorted section. How to get back? Have this sorted section property. So all these, all the elements here will have this property, and sorted section element set frame material still. Double star diameter, this means that how you calculate the area, cross-section area of the sorted section. So ABAQUS does not read this line, and it only reads this area information. So this is for truss. But if we say beam problem, you probably will have one more extern here as moment inertia, something like that. Material property, elastic, Young's modulus, Poisson ratio, and linear perturbation. As I said last time, you need to change the step as linear perturbation, and 10,000 Newton central load. Oh, okay, this one is important. So last time I said in 2D problem, 1 means x direction, 2 means y direction, and also remember we have UR3, right? UR3 means rotation about the third coordinate. So the third coordinate is z-axis. And if it's a 3D problem, you have displacement in x direction, displacement in y direction, displacement in z direction, and also rotation about 3 coordinates. So it is the first 1, 2, 3 means rotation, 4, 5, 6 means 1, 2, 3 means translation, and 4, 5, 6 means rotation. And it is in when you use boundary condition, how you fix degree of freedom, and also how you apply loads. You apply in y direction, in x direction, or in z direction. And also when you apply couple, the couple is about rotate about which axis. So this one is very important. Okay. So this is a definition of boundary condition in the amplifier. This is node number 103, node 103. First degree freedom, last degree freedom, and displacement value. So this first line means at node 103, I fix the degree freedom 2. What does degree freedom 2 mean? Yeah, displacement in y direction. So it means that at node 103, degree freedom 2, the displacement value fixed at 0. So it means in the last problem is roller support, right? All the other degree freedom are free, but you cannot move in y direction. And these three talk about the same thing, but the first 3 lines is the same thing, just different expression. So you can use either one you want. So the second one, 2, 2, also means first degree freedom, last degree freedom. But if there's no displacement value here, it means by default it's 0. And this one, 103, 2, it means that I only fixed 2, degree freedom 2. So this 3 lines is the same thing. You can use any one you want. And this one means at node 101, I fixed 1, the first degree freedom. It means displacement in x direction. And 101, 2 means I fixed the displacement in y direction. So for these two, if I want to write it in one line, how should I write it? 1, 1, 2. And the built-in constraint, you can also use this one. And encaster means all degree freedom are fixed. So in 2D problem, it means displacement in x direction, displacement in y direction, and rotation about the axis. In 3D problem, it means all 6 degree freedom are fixed. And hint means all translation degree freedom are fixed. It can rotate. So in the last problem, the overhead hoist, it means the node at this side is a pin joint. It's allowed to rotate, but the translation in x direction and the y direction is fixed. So this symmetry you will learn later, but not today. This is how you define the load, concentrated load applied at node 102. 2 means in y direction, negative 10,000. Negative, so it's downward. The force is applied downward. And our request, I remember I said last time, when you need to print out the stress information, you need to use the integration point, right? So element print, S means strain, S means stress, E means strain. And this result should print out at integration point. If you print out at the node, what should happen? What will happen? So you see last time in the contour plot, the stress is average at node, the average of the element collecting to that node, and between two nodes is interpolation, gradually change. So whenever if you want to know the stress, strain result, always use integration point, EL print. And node print is unique nodal, I talked last time. So if you want to know displacement, you want to know displacement and node. If you want to know the reaction force, of course, you want to know reaction and node. So end of step. So this is a full input file for the question last time, overhead hoist. And what else? So this is how you modify the input file. So for that problem, if, for example, I have 7 elements and I want to change the diameter of one element, I can set this 17 as a separate frame 2. This is frame 1, this is frame 2. And then I define the cross-section area of frame 2 as this number. So this is how I modify the input file. And so today I will do a 40 stress design. 40 stress design basically means that for a structure, when you apply load, it will show the stress. And then for some member, because for the initial structure, I use the same cross-section area for all the truss. But for some member, it will have very high stress. For some member, it has very low stress. And I have a allowable stress. So for the member who has a stress higher than the allowable stress, what should I do? Increase cross-section area, right? Make it stress decrease and make it below allowable stress. For some member, if its stress is way lower than the allowable stress, what should I do? Decrease cross-section area, because our objective is to minimize weight, right? So for the stress is very low, the member stress is very low, we decrease the cross-section area and then increase the stress and make it reach the allowable stress. And then we can get a fully stress design. So in the end, we can imagine that the whole structure for each member in the whole structure will have almost the same stress, close to allowable stress, but each member probably will have different cross-section area. That is what fully stress design means. I think this is what it is. So I will show you the problem. Right here. So this is a problem in your textbook. If you bring your textbook here, you can see it's page 97 or 98. I did some modification. So Young's modulus, 100 gigapascal. Poisson ratio, 0.3. I define node as 1, 2, 3, 4. And element, 2, 3, 4, 5. What else? Okay, cross-section area. So for the horizontal and the vertical, these three truss, it has cross-section area of 1 centimeter square. For diagonal truss, it has the cross-section area. And the loading condition is, I simplified it, so it's at node 3 and node 2. In x direction, 10,000 Newton. What other information do I need? And boundary condition. Okay. So this is a pin joint, and this is a pin joint. I think that's it. Oh, allowable stress. $80 megapascal. So this is our problem. This is a 5 trusses problem, and the boundary condition is this node and this node pin joint. And loading condition is at this node and this node, I apply 10,000 Newton force in the x direction. And the cross-section area for the horizontal and the vertical trusses, I use 1. And for the diagonal truss, any question?
I was wondering, how come you didn't define a node in the middle where the elements intersect?
I will say later. So the problem is there shouldn't be any node here. But when I use ABAQUS to sketch this problem, it will automatically generate a node here. And then I will use the I will modify the amplifier to remove this node. Because there's no way I can modify it on the graphic interface. The only way I can do it is using the amplifier. So I will show you later how to remove this node and also how to change this the cross-section area of each truss to gradually get a fully stressed design. Oh, dimension here. So the length of the truss, the horizontal and the vertical, 0.3 meter. Centimeter, meter. Be careful. So this is a problem. I probably will use this as homework. I don't know. So let's go back to ABAQUS. Since most of the procedures are similar to the one I did last time, so I will do it quickly, not in detail. First, create parts. 2D planar, deformable wire. And this time, because the length of the truss is 0.3, so I use approximate size as 2. So it doesn't matter. You can use. And you can draw like this. So because I didn't use coordinate, I need to add a dimension to make sure that this dimension is 0.3. And also, you can use this add dimension for all the horizontal and vertical truss, but as I said last time, you can try this one, add constraint. Add constraint, you can use equal length, and then select this one, and this one. So it's done. And you can see there's a little H here. It means horizontal, and V here means vertical. Define material property. Mechanical, elasticity, elastic. Young's modulus, 100 gigapascal. Poisson ratio 0.3. We will not use this Poisson ratio value, but need to enter it. And section. And be careful this time because last time all the cross-section area for all the trusses are the same, right? But this time I have horizontal and vertical and diagonal. They have different cross-sections. So I will not change the name here. You can change it later when you do your homework. So I will just use section 1 as for the horizontal and vertical trusses. The cross-section area is 1, E negative 4, right? And assign this section to this one, and this one. Section 1 just defined. And then I define the cross-section, the section for the diagonal, 0.25, E negative 4. And assign. And now you can see that what I want is this one and this one is one truss. But when I sketch as one truss, ABAQUS generates the node here automatically. So I will show you later how to remove this node by using the modify the amplifier. So right now I just assign the section for the diagonal trusses. Section 2. profile, as I said last time, for trust problem, you don't need profile. Profile is a cross-section geometry, so you don't need it. And the next step, assembly, you can just follow this model tree and to do step by step. Assembly, create instance. Mesh on part, mesh on instance, doesn't matter because we only have one part, one instance. Select any one you want. And create steps. Change this general to linear perturbation because general means nonlinear, yes. And once I create a step, the field output request is generated. And I showed you last time, for the trust problem, we want the displacement result and stress result, and it's already here, so we don't need to do anything about this field output request. We will change it when we do the bin analysis. But for now, we don't need to do anything. Apply boundary condition. Apply boundary condition on initial step. Displacement rotation, because this time these two nodes have the same boundary condition, so I can select the two nodes at the same time, and then fix what U1, U2. And boundary condition is done. Apply loads. Concentrated force at this node and this node. CF1, concentrated force in X direction, and no minus, it's positive, in positive X direction. What else do we need to do? Mesh. So for the mesh, first we need to define element type. What kind of element type do you want to use in this mesh? You see here, select region to be assigned the element types. I select whole region because the whole region I use the same element type. And changes to truss. And they say T2, D2. It means two-node, two-dimensional truss. Seed. So last time I used seed instance because last time all the truss has the same length, right? So I can use a global global size 1 for all the trusses, and it will automatically generate one element on one truss. But this time you can see that this truss has a different length. So what we can do is that if you still want to use one element on one truss, you can seed edges, and then select region to be assigned local seeds, select whole region. Is by number. And number of elements, it means how many number of elements do you want to use on one truss. So I choose this to 1. And then mesh instance. Okay to mesh the part instance? Yes. So if you want to know the mesh result, you can see that 7, can you see it? Okay, you can see it. 7 elements have been generated. So because it is supposed to be 5 elements, right? But because there's a node here, so it's 7 elements. And also you can go to View, Assembly Display option, Mesh, Show Node Label, Show Element Label, Apply. So this purple one, purple number is node label, and this yellow is element label. So I think all the everything's done. I create a job. Double click. Submit. Okay. So this is vomit stress, S11. And also, if you want to know the displacement result, okay, so this one is too small. Let's see. Viewport, main menu viewport annotation option. I can change this annotation to bigger size, 24 line. Okay. Any question? Okay. So now I will show you the input file. C temp job 1 IMP. IMP means input file. So I can start from here. Node information. There's a 5 node here, right? So what I want is only 4 nodes. So I need to remove the center node. What I can do is change the definition of node. Change this to coordinate. And then remove this 5th node. Delete it. Any question here? Any question about defining the node?
Isn't it 0.3, 0 for the fourth one?
What? Who is talking?
The position of both nodes, the coordinates.
X coordinate is 0, Y coordinate is 0.3. 0, 0, 0.3, 0, 0.3, 0.3, and 0.3. You have a question?
If you're writing your own input file and you're only working on planar analysis, do you have to put in the Z coordinate, or will it automatically
For 2D problem, because at the very beginning I already defined is 2D planar Y, I don't want to remember that. So for 2D problem, only X, Y coordinate. If it's 3D, you need to put in the Z coordinate. Any other question?
Should either 2 or 4 be 0.3 here?
Which one?
Because X and 4 are the same right now.
Oh, sorry. My mistake. Sorry. Yeah, 2 should be, X is 0.3 and Y is 0. Thank you. Any other questions in this part? Okay, so next we need to change the definition of element. So right now it has 7 elements. I can delete 6 and 7 because I only want 5 elements. The first node, the first element collect in node 1 and node 2. The second element collect in node 2 and node 3. Third, 3 and 4. I change this to 4. Element 4 connect in node 4 and 2. Element 5 connect in node 1 and 3. Any question here? Or did I make some mistake? Okay, so this is the modify the element. Now let's look here. Node set, pick set 2, internal generate. So node set means I will define a node set, and then the name of the node set is pick set 2. And internal means this is internally generated by in ABAQUS. It's not, I didn't define it, but it's internally generated. And generate here means, for example, 2, 5, 1. It means start from 2 to 5, the increment is 1. So it basically means 2, 3, 4, 5. You know what I mean?
The node numbering under the element has limitation to number it 2, 1 or 0 or 1, 2 or 2, 1 for any element.
Talk slowly.
While numbering the nodes for an element, for example, for element 1, it was 1 and 2, right? For the element 1.
Yeah.
It's like, does it represent the direction of like I to J or J to A like that, or we can name it in any way?
I just said you can define 1 to 2 or 2 to 1. The result will be the same.
It's same.
In this way, it means the local coordinates is from node 2 to node 1. But if I exchange it 1, 2, it means local coordinates from 1 to 2. But no matter how I define it, the final result will be the same, right? Any other question? So let's first see what the pick set 2, node set used in the later input file. You can see it, element set, node set. Okay, it's not used. Okay, let's check the element set first. So element set, EL set, pick set 2, internal, 2, 5, 6, and then it used as vertical and horizontal trusses, right? Because you can see the cross-section area is 1. But in my definition of node and element, it should be 1, 2, 3, element 1, 2, 3, right? I mean, these are the node label and element label generated by ABAQUS. Now I want to change it, so I need to change this element set to what? 1, 2, 3. So this element set 1, 2, 3 truss 1, 2, 3 will have the cross-section area of this one. Any question? So you can understand, right? And then for the diagonal trusses, I define it as element 4 and element 5. You can see here, this is the definition, this is the property of diagonal trusses. The name is pick set 3, element pick set 3 here. So I need to change this 4 to 4 and 5. Yeah. And node set pick set 1 and node set pick set 3, because it's not used in the later input file, so we can just ignore it or delete it. And this is this part. Any question on this part? Let's continue. Here, node set pick set 4, and we can check the pick set 4 is used for boundary condition. And here, pick set 4, 1, 1. What's the meaning of pick set in the boundary condition 1, 1 mean? Fixing x direction. And pick set 4, 2, 2 means fixing y direction. So since I know that this set is used for, this node set is used for boundary condition, I need to change this pick set 4 to 1 and 4. 1 and 4, right? And also, pick set 5, we can see that it used for here, loading condition. Pick set 5, 1 means apply in X direction and 10,000 Newton. C load means concentrated force. So I need to change this pick set 5, 2 and 3. I don't need to change it. Okay. Any question? So I assume everyone can understand it. And then what else do I need to change? I think it's done here. I think it's done. For removing the center node, I think everything's done here, and I will try save. And then since we changed the input file, we cannot use this one again, so I need to, let me delete this one. And there are two ways to run the modified input file. The first one is you can create a job, and as I said last time, you can use source input file, and then this one, job 1 INP input file, the one I just modified. Continue and submit. Let's see if there's any error in it. Yay. Results. Now we can see that this is one truss, and this is one truss, and the center node is removed. If you need to, you can go to Tools, Query, and Mesh. We can see that the information here, number of nodes, 4, number of element, 5, number of element type, T2, D2. So it's successfully changed. Any question? So after remove this center node, we need to change do the fully stress design. So we need to change the cross-section area of each truss, and then to see how the stress change and make the stress of each member getting close to allowable stress, right? First, let's check the stress first. As I said, for the stress, always use integration point, and S11 means sigma xx unit axis stress. Apply, and go to RPT. Here. Scroll down. So you can see here. For element 1 and element 3, we have the stress 92. So what we should do? Yeah, increase cross-section area to decrease the stress, make it below 80 megapascal. And for the diagonal trusses, it's 44. So we can reduce some cross-section area to make it increase, getting close to 80 megapascal, and also the weight of the structure can be minimized. And also for this term, the same. So I think I only have 5 minutes. Let's see what I can do. Let's go to input file. Element set. So first, I can for this I can. Why it doesn't work? Okay. This is originally for the horizontal and vertical, right? So because the two horizontal have the same stress, I can use them as a group. So and vertical as another group. So I need to. And I change this to element set, element set, element set, element set 4. And then also for element set, okay, this is really hard to. And change the name to element set 4. And the vertical is element 2. And also I need to remove 2 here. So you know what I'm doing here? Okay, good. And then for element 2, for example, right now if I want to change the cross-section area of vertical truss, because the vertical truss, it has only like very low compression, right? I can reduce a cross-section area. For example, if I change it to, oh no, here. And then for horizontal, I need to increase. What happened? And also you can do the same for the diagonal trusses. And so I just do a demonstration for the horizontal and vertical trusses, but for the rest you can do it yourself because I don't have time now. And try save, and let's see the result, how the result change. Let's go to the report. Stress, S11, apply, and RPT. Where is RPT? Let's see how the stress change. You see here, the stress of the 2 horizontal 1 and 3 decreased because we just increased the cross-section area, right? And also, this one increased a little bit. So you need still continuously doing this optimization process. And yeah, so this also changed a little bit. You need to change the cross-section area of each truss. Any question? So if no question, then that's it for today. Thank you for coming, and be safe during the weekend.